Yeah. Okay. So good afternoon, everybody. Got a question right there about scheduling. The advising scheduling. If you had Dr. Christie in the past, you will be shifted to somebody else. It's just distributed between the rest of us that are here. Um, I don't know if any of you have heard directly from Dr. Pardue. I think he's going to be sending it out an email pretty soon. Everything's going to be a little awkward this time. Just fair warning. I would just encourage everybody to make sure that when you go to schedule, you touch base with your advisor. I think the entire system that we have been using in terms of like making sure all of that is happening is changing because we're doing student workday, and potentially a lot of the class schedules are changing, not only because Dr. Christie's not here, but also because there's an effort for the college to change how many times courses are offered. So that could mean certain things have changed. I don't even know the full details of all that yet or where we are. So none of us will know exactly today, but hopefully we'll be having more information soon. Yeah.
So I assume there's a new way for y'all to like take the hold off of us and do stuff to fill out that paper.
Okay, so as far as I understand, well, I don't know. I really just don't know. I've heard something about it, and it sounds like that whole system of having the hold might not even be there anymore. I never interfaced with it directly aside from taking the scans, and so this is on the advisor end. I just pass that along to the department and somebody else checks it off. So I don't know what the structure of all that looks like, but it would be a good idea, especially given the changes coming up, that you get advising. So act like it, even if you're able to schedule like today, but then get your advising tomorrow, you go to revise something, just make sure you have an advising appointment. Just that's what I'm going to say. And we're going to figure out the rest of it. Okay. How did the Excel homework feel? Got it? Got up to speed with it? Great. Any questions on that? All right. If you were more prepared than I was, you would have noticed that the course page didn't have our today's slides till just now. I just uploaded them, so they're there now. So if you wanted to grab those for today, there they are, as of 2 minutes ago. Today we're gonna wrap up buffering and titration. And as you'll see, what I'm aiming for is to have us be able to appreciate what is this whole buffering thing about, and be able to see that it can be very quantitative, but sometimes we don't have to be fully quantitative, or we can just simply say, well, a buffer is going to be stronger under these conditions. Okay, so I'm looking for us to get to that point based on the fact that we've been talking a lot now about shifting acid bases around, the whole pH scale and what changes across it. So far we've looked at graphs that look kind of like this. Log of some concentration, or maybe alpha or log of alpha versus pH. We're going to flip things around a little bit today because sometimes it makes sense to watch pH as the thing we're observing as we add a known amount of acid. So given that, a couple of the plots are going to look a little different today, and we're going to kind of think about things in the manner that makes sense from that titration perspective of being in the lab, adding a known droplet amount of acid or base, repeatedly until something changes. So in the homework, the homework that's due Tuesday, you have a couple problems that ask for you to draw some titration curve, and I had at least one of you ask me about that. It's like, because I gave instructions for you to put pH on the y-axis, and we hadn't really talked about that yet. So we're going to talk about that today. You'll get a feeling for what that looks like. Okay, so we left off last time talking about this net strong base concept with Cb minus Ca. If the net strong base is negative, we've added a net strong acid. So we could add 0 base, and we're adding acid, and we get a negative net strong base value. It's pretty straightforward in terms of what that means. And so we had some discussion about these equivalence points, and we had this example we didn't quite get to. So I just wanted to read through it briefly to kind of refresh our memories to where we left off. Okay, I'm not too interested in us, solving this one right now because we have to talk about more of the buffering stuff. But we'll just kind of refresh our minds about the process here. So we have this example. It says for a system with the figure shown, consider a solution that is at pH 10, and then we want to know, or want to answer, A, what is the initial net strong base, Cb minus Ca? B, how much net strong base needs to be added to the solution per liter to lower the pH to 3? And then it goes on to explain, well, that's a trick question because we're lowering the pH, meaning we're adding acid. So that's a negative net strong base, which is what we already talked about. So the solution for this problem, if we look at the pH 10 condition, first thing we might want to do is just simply highlight, okay, here's what the spot we're talking about. So whatever we're dealing with is kind of along that line if I drew it nicely. So part A is asking, what is the initial net strong base? So we can kind of take a look and see from this figure the pH is higher than the NaA equivalence point. So NaA equivalence point, that is kind of the basic side of a acid, right, where the OH minus ends up equaling the A minus concentration. So if we follow the HA concentration. So if we follow the HA line, where it intersects the OH minus, that's the NaA equivalence point. That's what we get if we added simply some amount of this acid in the form of NaA, because it all comes out as A minus. So that would be kind of that spot. So if we look, our pH at pH 10 is to the right of that, meaning we are more basic. So we have more net strong base than if we added exactly so we're given some total acid concentration, right? So imagine this is acetic acid or something. If we added it all as sodium acetate, that would put us at something like a pH of 8. So we need more base than that, right? So we know we will have a larger amount of net strong base than 10 to the minus 3. Okay, so let's read on with this solution here. So the initial value of Cb minus Ca must be larger than that. And we can define Cb minus Ca as we have looked at in the past. This is going to be essentially all of the, if we set up an electroneutrality equation and took away all the inert stuff, moved them all to the left side, so all the cations and anions that are not participating, like Na plus and Cl minus. And then everything else on the right side, we'd have this stuff. So A1AT, this is the same thing as writing A minus. Okay? Plus OH minus, minus the H plus. So those are that's sort of the charge balance for all the stuff that is pH affected on the right side. And we could solve it from there, right? Because we know the pH is 10, therefore we know the OH minus. We know the H plus and the OH minus. And with that information and with AT, we can solve for alpha 1 and solve that, right? So we could put in all those numbers. We've done that. And then we could find our Cb minus Ca and it would come out to be 1.1 times 10 to the minus 3rd. Okay, does that make sense? Kind of have to remind ourselves that the definition of Cb minus Ca, right? Be like, okay, yeah, that's how we write it up. That's where it comes from. Okay, so part B says, well, what about pH 3? If we have the system, how do we get it down to pH 3? So first thing we could do is simply calculate what is Cb minus Ca at pH 3. And then compare that to how much we had at 10, right? So if we do the same process where we have alpha 1 AT plus OH minus minus H plus, we have an H plus value, we have an OH minus value, and we could solve for a new alpha 1 AT value, right, for a new value of A minus. We could also kind of look at the plot and say, well, at pH 3, the A minus concentration, it's starting to get pretty low. So maybe it would be fair to neglect it entirely. So we'll see what the solution says. Okay, so it writes it up like that. It does not say anything about neglecting it, so we'll just leave it in there. It puts in the numbers, and we get this negative 9.90 times 10 to the minus 4. Okay, so that's the amount of net strong base at that particular pH with this system. Okay? To get from one place to the other, we have to make up that difference. So we would have to say we're adding a negative amount of base, so we're adding some acid, and so we're going to end up, if we're putting it at the CB minus CA terms, we'll get a negative number. And that's okay, we just know that that's adding acid. So that means delta CB minus CA, we would just take the ending point minus the starting point, and we'll get negative 2.09 times 10 to the minus 3 equivalents per liter. Okay, does that make sense? All right. So that kind of primes us in a way to think about how are we moving around on the pH and what exactly is happening. And if we are going from A minus to, and I'm just going to write this as kind of the half equilibrium, right? If we want to get to HA, and normally we write this backwards, but just for the moment I'm going to write it this way. If we want to get to HA, we have to use a proton, right? We have to grab a proton from solution. So anytime we are having a species that is grabbing a proton from solution, that is essentially taking up an acid that you might add from some other source. So if we're adding a very strong acid to titrate our system, and we have a molecule in there that's going to grab it up as we're adding acid, we are buffering the system. We are taking away some of the acid so it doesn't just change the pH directly. So that's what we're doing when we're titrating. Whether it's an acid or a base, if it's something that can take it away, then it is slowing down the change in pH as we're adding that acid or base. So for every 1 unit of acid that we add, if there's nothing in the water, we shift the pH by that same amount of units, right? However, if we have something in there that's gobbling up the H+, then it's not so straightforward, right? There's equilibrium involved. Some of it has to go to the HA, and some of it's going to shift to pH, and we find a new equilibrium, and then that keeps happening. Okay? We can push through it and add enough that we titrate it. That is our titration. So if we call it an alkalimetric titration, we're adding a strong base. So we're heading up the pH scale, and we could do acidometric, going down the pH, we're adding an acid. So the little graph over here I have on the right, we see, is this acidometric or is this alkalimetric? Yeah, and if you look at the x-axis, it's labeled for us already, right? But we could label this actually as net strong base, and then it's not as clear. I guess with the units it would still be clear. So we see here there's a base. NaOH is a strong base. However, you can just look at the shape, right? As we're adding more of whatever it is we're adding, we are going up in pH. So upward is basic. But we could have an acidic titration, acidometric, and it would look very similar, but it would probably, or it definitely would be going in the opposite direction. And now I've just confused that here. So let me do this. And if we were going in the downward direction, this would be acidic. Okay, so fairly obvious, but we do need to do a little somersault with our brain about putting the pH on the y-axis, right? So we start thinking about what is happening to the pH when we add some acid or some base, right? And as we add more and more base, we are getting more and more basic. The reason it's not just linear is because it's not just pure water. There's something else in it that's doing that buffering, right? So in the scenario where we have HA in equilibrium with H plus and A minus, well, every time we add an OH and we are adding to the system, if there is some HA, well, what might happen is we might take that H away to form water, right? So this could end up giving us H2O and A minus, would be a way to look at that, right? So in that sense, every single HA molecule in there is scavenging an OH minus that we're trying to add when we're adding base. So either way we go, if we have this weak acid or a weak base that is taking stuff, interacting with stuff, it's slowing down the effect of adding a strong acid or a strong base. This is why it's really difficult if you go into the lab to say, oh, okay, I want a solution that's pH 3.3. It's really difficult to just add exactly the right amount and get it, because your pH will tend, like a little small bit of error would change it a lot. Or if there's something else in the water, it's going to change this dynamic a lot. So you typically have to use some sort of buffer, as we'll talk about today, to give you a region where it actually takes a fair bit of acid to make some change. So if you're a little bit off, it's pretty stable. You're now at 3.33 instead of 3.30, and that's probably good enough. So there's a lot to buffering, and if we think about treating, let's say, river water for chlorination, and we need to shift the pH to a good range for chlorine, so we get the right kind of chlorine, well, we kind of have to know how much acid are we going to have to add. That's going to depend on what are the natural constituents to that water, right? If there's a lot of alkalinity, a lot of mineral content, a lot of carbonate, it's going to be a little harder. We're going to have to add a little more acid to do the adjustment that we need, okay? So it shows up in a lot of spots, and of course in a lot of chemistry experiments. If you're in a chemistry lab, you've probably done this titration, and hopefully this will make a little more sense what that titration is doing. So we're going to use a small volume. We talked about this already. We just want to use a fairly high concentrated solution of acid or base, so we can use a very small volume of it. So we're not diluting the system, because that just complicates things a bit. And what we're going to do is sketch this titration curve. That's how pH is changing as we add some amount of titrant. So when the homework tells you to sketch a titration curve of X, Y, or Z, that's what we're doing, is we're thinking about how is the pH changing as we're adding some net strong base, or some, whether we're adding acid or base. Okay. Another thing we can do on the x-axis is we can consider using some different labeling, right? So far I have just adding some volume or some moles of base. But we could also consider these equivalence points and those little F or G fractions that we talked about last week as a way to guide us. So I'll bring up a slide to remind us real quick, but the G and the F correspond to the changes in our HA and the NAA equivalence points. So the amount of acid we would need to add in order to get to the HA equivalence point, or the base to get to the NAA equivalence point. So here's an example with a total acid concentration apparently is 0.001. So we'd have to add that amount of base if we started at the HA equivalence point to get to the NAA equivalence point. We talked about that before and how that's kind of defined. And the G is I guess the fraction on the acid side is the fraction of acid in solution compared to the HA equivalence point. And the F then is the inverse of that. It's the fraction of the base. So we talked a bit about that. I have, oops. Oh, sorry. I wanted to show one little thing, and I forgot I animated it. This little, the plot down here, we could just simply write as CB minus CA, right, instead of putting a base. Of course, we'd change the units, and that might change the scale there a little bit, but that's going to be actually quite typical, is to put that as the net strong base down there. But we could also use, so we could use any of these here as the x-axes. Okay, so any way we look at it, we're just considering where we're going with the amount of acid or base with reference to how much does it take to get us to different equivalence points. So any of those could be used as an x-axis there for us. Okay, that brings us to buffering capacity. I'll come back to F and G, kind of remind us and connect these a little better again. But buffering capacity is that aspect of the fact that they are taking away protons or OH hydroxides from solution as we add it. So a buffer slows down that change in pH or H plus that is in solution, right? So of course we have a mass balance on H. We're not changing. If we're adding some hydrogen, it's not just magically disappearing, but it's associating with molecules, and therefore it's no longer in solution. The brackets kind of imply this because that's aqueous concentration, but just to be clear, I'm going to say in solution here, right? So free floating in a completely pure water system. We've done these problems before. I say add 0.5 moles per liter of HCl, then we can just assume that we have 0.5 moles per liter of H plus. That's not necessarily true if we have something that has some buffering capacity. So the slowing down of that change is what we're interested in. So if you look at this graph, if we are adding some NaOH, some OH minus really, at some pHs, or excuse me, at some amounts of base, it's not having a big change in pH. We add a lot of base for a small change in our pH. Then eventually we get a huge change, a fast change in pH, several orders of magnitude with a very small change in base. Okay, so at some point it becomes very effective. Then we come back to a situation where we are barely making any progress. The more NaOH we add, well, we're barely getting anything further than pH 11. Okay, so these are the dynamics that we want to understand. So on this type of a plot, we can describe what's called the buffering capacity, also sometimes called the buffer intensity. It's the same thing as this uppercase beta. We can define it as essentially equal to the slope on one of these plots. But it's written a little strange. This is the, I guess, the inverse of the slope when we do the plot as pH versus NaOH. But it's the change in net strong base to achieve some change in pH. Okay? So the reason we plot it this way with pH on the y-axis is because that's often what we are observing. But sometimes it still makes sense to look at it the other way. So I'm not, we're going to follow some conventions here and work to understand and make intuitive sense of it. So you can see here that this is a small slope, a very large slope, and another very small slope, right? So we can tell that there is something happening here. So let's take for a moment three different conditions, 1, 2, and 3. And just think for a moment. Well, first of all, in all cases, our buffer intensity should be greater than 0. And if we take a look at the way we've written this, if we have a negative change in pH, that means we're adding acid. That means this is essentially a net 0 for the base, or a net negative for the net strong base. So a negative on top and the negative on the bottom. So anytime we are going down the pH scale, the numerator is negative. That's just by definition, right? So this is always going to be a positive number if there's any buffering, and chances are there's going to be something buffering. So with that said, let's take a quick look at case number 1. We have a large change in the numerator, so we're adding a lot of base, and a small change in pH. So therefore, our beta value, something large divided by something small, is even larger, right? Or is still large at minimum, right? So it's relatively large as far as we can see. That same trend holds through for 3. Large change in amount of base over small change in pH. So again, our beta is large. And for 2, it's reversed, right? We have a small change in net strong base made a huge change in our pH. So this would be small over something large. And so in this case, beta is small. Okay, so in this particular scenario, we can say something about the buffering capacity as we arrive at different amounts of base that we've added. Okay, so we're going to work more on this in a couple slides, flesh it out a little further, but I'm just kind of trying to show you what we're looking at is that dynamic of when and how things are changing. And the buffering capacity does change as a function of, well, we would normally call it as a function of pH, right? So if we are making use of, let's say, the HA system, right? HA in equilibrium with A minus and H plus, you know that at some pHs we have a lot of HA, and so that could consume a lot of OH minus. But if we're already have very little HA, it's not going to do anything to buffer that so much. It's not going to have some impact. So we don't really know what this plot is showing in terms of what's in solution, right? This is just a very generic thing. So we will move forward and look at some more precise things and kind of work to understand what's going on accordingly. So here we have something with a pKa of 9.24. So this time we do have some acid in solution. So weak acid, or I guess maybe even a base. But it's going to have that buffering capacity for us. And it's drawn up here with the pH on the y-axis and the net strong base on the x-axis. So there's a couple points I want to highlight here. The distance between certain parts of the curve are going to tell us something very helpful about how much stuff we have in solution. So it turns out that there are inflection points as we draw these curves. There are areas where it's concave down and areas where it's concave up. And I'm not going to trust my drawing. I have a plot of this that just shows it very nicely. And this one, we just don't have a ton of data points here, so it might be a little hard to see. But essentially, we have an inflection point approximately here, because it's going from something that looks a little bit flat or maybe concave down, or excuse me, up, to now concave down, right? Can anyone else do that with your fingers? Am I weird? can go back pretty far. Yeah, I've got flexible joints. It's funny. Okay. Yeah, so sometimes it's funny because I don't think about it, and then as I was like making my gestures, it's like concave this way, concave. It's like, oh wait, no, I'm a weirdo. Forgot. Okay. So we have that on this right portion, and that's that point where it changes, that's called an inflection point. That's gonna be our NAA equivalence point. Turns out that always holds true based on how the dynamics of the system go. Likewise, on the other side, we have another inflection point where we are too sharp for my fingers, going up, concave up, and then it's converting to a concave down, right? So at that point, we have another inflection point and therefore another equivalence point, which is our HA equivalence point. So we've got two, so this is our NAA equivalence point and our HA equivalence point. So that means we now know something about, if we can measure that distance based on the base that we're adding with our little titrator thing, that actually tells us something, because what we're doing is we're measuring the amount of acid that's already there by adding some base that we know how much we add, which turns out to be very convenient if we can pull that off. So this is the reason we do titrations in a lab. And of course, we don't know that until, almost ever, until we have this class, right? Or really until you teach the class, because I didn't even feel like I knew it until I was going through it. Probably knew it at one point, we'll just assume that. But that's a very handy way, by adding something, to see, okay, well, how much of this stuff do we have? How much of the A total do we have in there when I'm adding something different and I just have control over how much I'm adding? So this measurement that we can make, we can find it by watching what happens to the pH when it jumps and then it stops jumping, right? If we can take our measurements carefully, we can find that jump from F is 0 to F is 1, which is that crossing from the equivalence point to the next. That make sense? Okay, so here's my reminder. We defined F and G basically as a function of, or as the fraction that is the amount of base that we add compared to the total concentration of the unknown acid, AT. So we're adding, let's say, sodium hydroxide, or we could even add some base like hydrochloric acid. But what we're testing is, let's say, the amount of bleach in solution, which is a weak acid. You did this with the Excel sheet, right? You had HOCl. That is something maybe we want to know how much is in there, in our drinking water, for example. Well, in order to find that, we're just adding some other type of acid that we know how much we have from a lab container. And if we do this right, we can then find some equivalent fraction. F is that concentration of the base that we've added divided by the concentration of the unknown acid in the volume. And that volume has to change a little bit. So we did this little caveat to say, well, we're adding a little bit of volume by titrating, so we can adjust for that. Or maybe we can do a very high concentration, small volume addition into a large volume of the solution. That helps too. At any rate, this is the deal. And I did correct this. I think I had something slightly backwards the first time we went over it. G is 1 minus F. And so at the HA equivalence point, G is 1, F is 0. And at the NAA equivalence point, G is 0 and F is 1. So it's just a fancy way of describing where are we in relevance to the equivalence points, and we can go beyond or below them. Okay? So a couple noteworthy things about that. So if F is 0, that means our net strong base is 0. That's our HA equivalence point. It's kind of the acidic side. At F equals half, 0.5, this is typically our inflection point. Let's see. Does that make sense? No. Don't ignore that. I think that's completely wrong. I made a mistake last time, and I didn't catch that on my talk here. So we're going to ignore that. The inflection points are happening at the equivalence point, so that can't be true. But we do have a couple of equations here that we can use to define, again, the CB minus CA. This is kind of where we started the class today with that example. Just kind of a reminder that the left is, we take all the inert stuff, any of the bases or acids, like if we do NaOH, the Na is showing up here in terms of the charge balance, or if we do HCl, the Cl minus would show up here as the charge balance. They're no longer acting as, or changing with a function of pH. Everything that's changing as a function of pH is on the right side of this, and each side, we can set that up as an equation. Okay, and we can also write F in similar terms as well by saying F is basically that net strong base divided by the acid, and so we can get that same equation divided by acid, and there we go. So a couple derivations there might be a little bit helpful. Just reminding you, this is kind of where these two pieces connect, right? So that example we started with is really the same stuff we're dealing with. Okay, so here's a good picture of the inflection points with it all very well labeled, and it's described here with this figure caption. It's probably a little too small to read, but if you really want to know every detail, I think if you download the PowerPoint, you should be able to read it. The point is we have different inflection points on this particular graph. What we have here is some system where we are going through adding some net strong base. We have this concave up. See, when we see the Cu, that's concave up, and we see CD concave down. And if you recall the little figure that we had a few dots on, it probably should make this shape theoretically, but we just didn't have enough measurements. Okay, and that's probably true for a lot of systems. It will be hard to get that precise, that much precision and everything. For this case, we have a system that apparently it's working well. Our pKa is 7. Our acid total concentration is 10 to the minus 3 moles per liter. And we can then take a look at what's going on. So in region 1, we are in a pretty acidic condition, meaning we have a negative net strong base. And every time we change some base, we don't have a big change in acid. Okay, so this is a log plot though, so it's probably a 1-to-1 because we've consumed all the buffer, and every time we're adding, let's say, more acid, it probably is having a kind of a 1-to-1 effect, but it's a log scale. Now, when we get to this inflection point right here, we see it's going from the concave up to the concave down. That first inflection point is our pKa. That's not our pKa, excuse me. Our HA equivalence point. And I now see my confusion from a moment ago. There is another inflection point here. I guess there has to be 3. It's got to be an odd number, right? It's got to be either 1 inflection point or 3 on a curve like this, because it has to be, this would be kind of 1 inflection point. In order to have 2, we actually have to have 3. So I'm going to revise just a little bit. This is probably our pKa. We'll come back and we'll double check that. Okay, so if we look at this graph that's very nicely drawn, we see that first inflection point, there's another one here, and a third one here. That third one is going to be our NaA equivalence point. And these are going to be the critical spots. So if we look up over here, again, it's not a whole lot interesting is happening. We're adding some base and we're having a small change in the pH. What's interesting is when we have these two cases, 2 and 4, that we have a small change in base corresponds to a big jump in the pH. So those are interesting spots. And I would also say in between them where we have a slowdown, that's where the buffering is really happening. And that's the interesting point where we have the highest buffering capacity. So when that F value is about 0.5, that is typically the highest highest buffering capacity. Okay, so in this system, the pKa is 7, which corresponds directly to this guy. So I'm pretty sure that when I misspoke here, it was really to, I had been looking at this plot and thinking to myself, it kind of looks like 1-ish inflection point, but we need 2 somehow. Really, there should be 3. And the middle one should be our pKa. Okay, so I'm just going to verbally correct that a little bit. This is the plot that really makes that clear. So, and you see labeled here B max and B min and another B min. So what we see here is the buffering capacity or buffering intensity is the highest when we're near the pKa or at the pKa. So if we are at the pKa, that means that we have an equal amount of HA and A minus. So either way we go, adding acid or base, it's taking a lot of acid or base to really shift the system. Okay, does that make sense? And you kind of see why, because they're going to scoop up the extra H's or the extra OH minuses. So when we are at the maximum buffering capacity, we could say alpha 1 equals alpha 0, or we're close to that, and that would be 0.5 in this case. Or we could say A minus is equal to HA. And we'll see, we're not going to work on quantifying directly the buffering capacity, but we will see an equation that we could use for that, and we'll see that we have to deal with where on this plot are we and what makes sense. It'll depend on these alpha fractions to an extent. For the homework, you do have a problem, at least one, that asks you to rank the buffering intensities. Okay? So this is the type of stuff you need to apply thinking-wise to that. It will matter how much A total you have, but what matters perhaps more than that is where we are on this scheme with reference to the pKa. Right? If we're at the pKa, we have an intense buffer, so strong buffer. If we are at one of the equivalence points, we are further away. We have a weaker condition. Okay? So the text in this snippet from our primary book says, in general, for any acid-base system, beta is the greatest near the pKa values and smallest at the pure acid and pure conjugate base endpoints. Okay, does this make sense? Okay. So, could we calculate it? Yeah, we could. Are we going to? No. Just a quick look at what it would take to get there. And perhaps this would be a little interesting. So if you are interested, feel free to let me know. And I can provide you some resources, point you in the right direction. This is from one of the other books that I use occasionally. We could take a log plot of the buffering capacity and look at that versus pH. That would give us some interesting things, and we could see these zones showing up and seeing what does the buffering capacity depend on. It's like 3 or 4 different functions that in certain regions one will dominate and others it won't. So there's some fancy derivations that take 2 or 3 pages to go through. if we wanted to. They arrive at this function, and it gives us, so some function of H plus some function of OH minus plus some function of these alpha fractions. So what you'll notice is one of them is going to dominate when H plus is high. So when we're at a very acidic condition, the others don't really matter. When we're at a very basic condition, the middle one's going to matter, and the other two won't really matter. But what we're really interested in is when we are near the pKa, right? That's the one that we're going to be most interested in because that's where the action happens. And you'll see this depends on both alpha 0 and alpha 1. So at an extreme pH, one of these two is going to close to be 0. And so that whole function goes close to 0. Okay, so that means this part of it would be the way to calculate a buffering capacity at a spot where it's near the pKa and relevant in that manner. So I'm not going to really ask you to do that, but you can see the 2.303. That's probably coming from a natural log or e to some deal with that with the derivations, and we certainly could calculate the two alpha fractions at the pKa. That would be 0.5 times 0.5. So we'd have a very simple equation at the pKa. So maybe if I test you on this, I'll give you that equation and tell you we are at the pKa, so you can use this equation. You can use this part of the equation, right? But I don't think I will test you anything really further than that. We're definitely not going to bother with any of the derivation or really messing with this part. You can see it when we take a look at the graph here. There are regions of pH where it seems like there's only one thing happening. And then there are regions of the pH where it seems like several functions are interchanging in terms of how this thing is moving, right? So just pointing that out, those are the kind of the transition points. And we're noticing that if we looked on the x-axis here with F, we're noticing that near where F is 0, 0.5, and 1. Okay, so those are the interesting spots here. Okay, so let's come back to this little graph. This is actually coming from an example of our book, in our book. So let's take ammonium and consider we have 1 liter with an unknown, 1 liter of solution with an unknown ammonia concentration, NH4+. We can determine the amount of ammonia in it if we do some titration. So let's do the following. First, 0.01 moles of strong acid are added by introducing 5 milliliters of a 2 molar HCl solution. The pH is measured and found to be 2. So what do we do first? We acidified it. We just made it very acidic and started at pH 2. That way we can titrate upwards. So this is pretty common practice. We're just going to blast it with a bunch of acid, see where we're starting, and march on upwards from there and watch what happens as we do. So we then begin to add NaOH, which is a strong base, in increments of 0.0025 moles, that's half a milliliter, of a 5 molar solution. So highly concentrated, small amounts that we're adding, and as long as the pH changes a little, like small changes, and then once we start seeing the pH start change faster, we just start adding smaller amounts, right? So we're just going to try to add a little less. So early on, we need to add so much, we might as well, drip in a lot. You probably remember this from chemistry, right? At first, when nothing's happening, you're like, all right, hurry up, hurry up, hurry up. But you have to be careful because as soon as something starts happening, you should slow down and take more careful measurements. Okay, so it's explaining all that when the pH changes rapidly. And here we have a list, the resulting concentrations. This graph is showing us of the strong base minus strong acid. Okay, so the next page I have this continued, but what we're looking towards is finding the ammonia concentration, right? Any thoughts on looking at that figure, what we could do? answer is kind of already up there in a way. Yeah. So the distance between the inflection points is the information we get about the acid that's doing some sort of buffering. So whenever we're talking about this A total, that's some sort of weak acid, or in this, or weak base or whatever, something that's interacting with the acidity, and we are adding some external strong acid or strong base to titrate it. So we are titrating this A total, and the inflection points and therefore equivalent points have to do with what's happening with A total. So when we go from one to the next, there should be some distance there, and that should be our concentration, right? So that's kind of where we're heading. I'm going to go ahead and read through the rest of this with you so you can see the other little details that it fleshes out. So the resulting concentration of strong base added minus the resulting concentration of the strong acid added. That was partly from the previous line. Okay, and the resulting pH, the titration curve we made is shown. The titration curve provides information about the system being titrated, the two inflection points on the graph, where the curvature turns from concave up to concave down. And again, I think there's technically probably a third inflection point here. It's just hard to see, which is why I was a little confused earlier, right? It's like kind of does that swoopy thing, but it's just a very small one in the middle. Okay, and that distance between those two inflection points, the obvious ones, that turns out to be 0.01, so we had to add exactly 0.01 moles per liter of our base. And that's something we are tracking, right? If you recall doing this in chemistry, you're adding it drop-wise and watching on your little burette. Okay, now we just added 1 more milliliter. What's the pH? Okay, 1 more milliliter. What's the pH? So we're tracking that as a function of how much we're adding so that we can figure out the amount of base required to get there. Okay, so that gives us the total concentration, in this case, that 0.01 moles per liter. This would also be true if we had a polyprotic system, so like the carbonate system or something. We're just going to have more inflection points, and we'll step through more of a roller coaster, right? So all of these concepts will still hold true and can be useful. Okay, at Cb minus Ca equals 0, the pH equals that if we had added 0.01 moles per liter of NH4Cl to the water. That's the acidic form of ammonia. Then we could say, thus this is the pure conjugate acid endpoint of the system. When 0.01 moles of base have been added to the system, that's the equivalent point has been reached. That's the pure conjugate base endpoint. Okay, does this make some sense about how we're dealing with titration curves now? What they're useful for? Okay. So I think I already had basically this up there already. One little caveat is we can account for the volume that we did add. We normally just set up a system so that we're not changing the volume very much and we can neglect it. But if we wanted to really be precise, or if we couldn't for some reason have a large volume, something like that, we could definitely account for that just with the change in volumes accordingly. So we are changing the amount of the acid concentration that we're trying to observe by adding something to it, right? Even the pH addition at the start, we added acid to start it at pH 2, we would need to count for that 5 milliliters, right? So we could go back and do all of that in our calculations. Okay, there's a couple of extreme cases we could consider about what they look like on a titration plot or curve, and that would be what happens if we try to titrate an extremely strong acid and an extremely weak acid. Okay, so Ka for this acid that we're observing is very large or it is very small. So pKa would be for case 1, since this is negative, pKa would be maybe negative, and pKa would be large, right? So when we have a pKa, a very strong acid like HCl, the pKa is negative or close to 0, right, on the pH scale. So case 1 is an exceedingly strong acid. So our Cb minus Ca is still atotal. Well, it's not still atotal. In this case, we know it's all going to be in the form of HA. So atotal is just, it's a very simple calculation there. Does this make sense? This is not making sense to me. Hang on a second. So normally we would write in a solution of HA, Cb minus Ca is equal to A minus plus OH minus minus H plus. So that we could rewrite the A minus as alpha 1 times A total. I think is this backwards? Or is this maybe when we've added enough base? Oh, this is obvious. Okay, I'm sorry. I'm just not thinking clearly. So when we have an extremely strong acid, like HCl, right, we put it in water and it basically goes completely to H plus and Cl minus. Okay, brain fart on my part, I'm sorry. So that means we are almost all in the A minus form at any pH. Okay, so that's why when we would normally write this electroneutrality equation as A minus here, this alpha is going to approximately 1 for this very strong acid, extremely strong acid. That's why we basically call it all atotal. A minus is approximately atotal. Oops. For an extremely strong acid. Okay, and likewise, in the inverse, in an extremely weak acid, at almost any pH, on any condition, it's all in the other form. It's all in HA. Okay? So that means the amount that is in A minus is 0. So we put a 0 there. Okay, so those are the two extreme cases that we could look at, and we can graph them. And if we put these on titration plots, we could see something kind of interesting happen, where their shapes are going to be arranged accordingly. So if we have something on one extreme or the other, there's not a lot of interesting buffering happening in between, right? The interest that we typically have has to do with the fact that H can exchange with A, right? And it's going to consume OH minus or it's going to consume H plus in order to move anywhere. In both of these extreme cases, there's not really much going on. So all of the interesting stuff in the middle has kind of dropped out, and we just have this swooping curve. And one would be kind of towards the HA equivalence point, and the other would be on the NAA equivalence point. So if we look closely, we can see for a 10 to the minus third acid concentration, we have an exceedingly large Ka here. So this is our extremely strong acid. And this would be our extremely weak acid on this side. So I don't really have a lot to say about it aside from we can recognize that these pieces are coming together, and in these extreme cases, everything's a little more boring in terms of there's not much buffering happening. Okay. Now, if we had a range of pKa's and we wanted to take a look at how they show up on titration plots, we could plot several similar systems, right? and look at F equals 0, F equals 0.5, and F equals 1. So if we have a monoprotic acid system and we have different pKa's, we will see where the middle inflection point arrives. Okay, and we will normally have them, I think, unless we get kind of extreme, right? Those last examples here, these are extreme and they have just the one inflection point right in the middle. So as long as our pKa is somewhat towards the middle, I guess when we're getting to 11 or 3, we're kind of getting far away. So they're a little bit extreme there and we don't really have an inflection point, but anywhere between these guys, we see a middle inflection point, and we can find the pKa by drawing that across. Okay, last thing I want to mention here is there's something called a grand plot. These are used for a more accurate determination of when do we find our endpoint. Sometimes we don't add enough acid in the experiment that we did. We didn't go down below pH 3 because we were just pouring and pouring and just wouldn't get there and we got bored and stopped or something like that. You know, well, there's a convenient way. Somebody by the name of Gran, it's named after somebody, made this plot, and essentially you can take your titration curve and then draw on top of it a function of 10 to the minus pH. It's a little funny to say that, but if you draw that curve and then take the straight line part of it and extrapolate that down, that'll get us to the exact amount of volume that would match our inflection point. So if this is our inflection point here, that's a way to quite precisely get at it, even though our pH never really went down to the level where we perhaps needed it to get to. So it's a way to find that titration endpoint. I'm not really going to ask you to do anything with that. Just wanted to let you know. I thought I might talk more about it and decided wouldn't really make a deep dive there, and none of the books really covered it in much depth. So it's something that's out there. It relates to these titration curves, and so there's definitely some information out there if you ever need it. Okay, I think that's all I've got for you today. Any questions? Yeah.
Could you go back to the exceedingly strong weak acid slide?
Yeah. This one or this one?
The one you were just at.
Okay, so we'll have the homework on Tuesday. That'll also double as an exam review. So come with any questions. And if you want, I can also probably take a look at the Excel stuff. I think you probably had enough from the workshop, but do let me know if you have some residual confusion or anything like that. All right, have a good weekend.